Okay, so I wanted to introduce some of our recent works on learning essentially low-dimensional polynomials using two-layer neural network trained by gradient descent. This is joint. By the way, can everyone hear me? Okay. Okay. All right. So this is joint work with Jason at Princeton, Kazusato, Eugene, and Taiji at the University of Tokyo. Okay, so the class of model that we will be looking at is a single index model on Gaussian data. So my input data x is drawn from Gaussian in d dimensions with identity covariance, and my target function f star only depends on a one-dimensional projection of this of my input. So this direction is given by theta, it's in Rd. So the way to think about this function is that, so I'm looking at so we should take d to be large. So my data is high dimensional, but the target function f star only looks at a tiny slice of it. It only looks at one dimension. So in order for an algorithm to work efficiently, essentially there needs to be some adaptivity towards this low-dimensional structure in the target function. So therefore, this model class has been extensively studied in the deep learning theory literature to try to sort of understand how neural network trained by gradient descent can adapt to this kind of low-dimensional structure via gradient descent. Okay, so for this model, we need to learn there's essentially two different set of things we need to learn. We need to find the direction theta, and then on top of that, we need to learn this unknown nonlinear function sigma star, which is referred to as a link function. And in this talk, we're going to restrict the link function to be a polynomial. I'll explain why this is very important later. OK, so how hard is this problem? Intuitively speaking, since I'm estimating d parameters in this direction theta, and on top of that, a univariate link function should be easy to estimate. So information theoretically, I need roughly d samples, right, to estimate d parameters. And this turns out to be sufficient, even without knowing what the link function is, even without this polynomial restriction. This information theoretic limit does not entail that there's a tractable algorithm. Right? So it's possible that without knowing the structure of the link function, you need to spend exponential compute in order to obtain this optimal statistical complexity. Okay, so now we're going to put more constraint on the class of algorithm we consider. So the classical, one of the baseline that we often compare against is this non-adaptive method, so linear estimators or kernel models. So these models, they're not really adaptive to this low-dimensional structure of the target function. So then we expect the sample complexity to sort of not be very, so they should suffer from the curse of dimensionality in some sense. So it's known that if I have a kernel method that's rotation invariant, then if I'm learning a single index model with degree p, roughly I'm going to need n equals d to the p samples. Okay. So this means that when the degree of the target function is large, then the sample complexity of kernel model would be very large. Okay. So basically, we see a gap here. So information theoretically, this problem should be solvable using just d samples. Well, if I have a non-adaptive method, I'm going to pay cost as d to the p, where p is a degree. So the question that we're interested in is what is the computational complexity of an adaptive algorithm? And in particular, we'll be looking at a neural network optimized by gradient descent. And we do not allow ourselves to spend exponential compute. So this will be like a polynomial with neural network. Okay. On this topic, so the prior results that essentially show that the complexity of gradient-based training of neural network is governed by this quantity known as the information exponent. So because we're working with the Gaussian data, so we can expand this link function sigma star using the Hermite polynomials. So we get a bunch of Hermite coefficients alpha I star, and the information exponent of the link function is defined as the index of the first non-zero Hermite coefficient of my target link function. Okay. So intuitively, if we write this, so for example, by definition, because if my sigma star is a polynomial, then this Hermite expansion is going to stop at degree p. So the information exponent is always less than or equal to the degree of the target function. Okay. And just to give you an intuition of why this quantity is important for gradient descent, so roughly speaking, this quantity, it measures how much information you have in the gradient around the random initialization. Okay, so here I'm computing the population gradient for one neuron. This one neuron being sigma x inner product xw. Okay, so this is the gradient of the correlation loss, and it roughly looks like this. And just by Stein's lemma, because x is Gaussian, you can take this is equivalent to the expectation of this derivative. And when you take the derivative of the link of f star, then the direction theta pops out. Okay, and then you have the scalar inner product. That's this expectation is essentially an inner product between two single-index models. Okay, and for this inner product, we can expand it using the pyramid polynomials, and what you get is essentially a weighted sum of the inner product between w, this is my initialized neuron, and theta, the target direction, raised to the s power. Okay. And the key observation here is that because I'm looking at random initialization, so this w and theta, they're going to be almost orthogonal. Okay, so meaning that if so this inner product roughly scales as d to the minus 1/2. So if I raise it to the i's power, then this will be d to the minus I divided by 2, which becomes smaller as this exponent gets higher. Okay. So in other words, if my information exponent is large, that means so if my information exponent is say like k, this means that the first k minus 1 term in the sum is 0, okay, because this coefficient is 0. So I'm going to start with a term that scales with d to the k divided by 2, which is small. Okay, so this information exponent kind of measures the magnitude of the expected gradient at initialization. So how do we translate this to a sample complexity? So roughly speaking, so the information exponent tells you that the population gradient at initialization scales with d to the minus information exponent divided by 2. But in order to concentrate the population gradient, so this is the typical, so we estimate the gradient from training data. Okay? And this concentration error, because we're concentrating a vector, this is roughly going to scale with d over n. And if you equate these two, the scale of concentration with the scale of the population gradient, this tells you that you need roughly d to the k samples to achieve non-trivial concentration. Okay? So this is how the information exponent relates to the statistical complexity of gradient, gradient descent. So in fact, so in the past year or two, there's been many works that show that if you give me a two-layer neural network and you optimize that gradient descent, then to learn a single index model with information exponent k, then n equals d to the k samples is sufficient. Okay. Again, because the information exponent k is always less than or equal to the degree p, and d to the p is a complexity of kernel model, we know that this neural network trained by gradient descent is indeed outperform kernel. Okay, so because of this adaptivity. But on the other hand, so this also tells you that because k can be arbitrarily large, right? If I can construct a target function with high information exponent, this means that there will be cases where this gradient-based training does not match the information-theoretic limit. Okay? But these are sufficient conditions for the sample complexity. So basically, they're not necessary. So the question that one can ask is, well, does this notion, does this information exponent capture some kind of intrinsic computational barrier for learning the single index model with gradient-based methods? So here's one way to think about it. So if we look at the gradient, this is related to the derivation in the previous slide. If you look at the gradient of the squared loss, then essentially you're going to have two terms. Right? So there's one term that looks like the correlation between y, this is my label, and basically the derivative of my of my student neural network. So this term is referred to as a correlational query because you're trying to gain information of the target function of the labels y via this correlation. Okay, you're computing this inner product with some function. Okay, and there's also another term. This term comes from fx squared. This term does not depend on the target function. You can evaluate this just by having the student model. Okay, so if you believe that this is a big if that neural network with a squared loss is actually learning by using this correlation term, then a way to measure this computational hardness is to sort of count how many correlational queries I need to make in order to learn the single index model. Okay. And so this naturally brings us to this class of statistical query algorithm, SQ models. So basically, an SQ model is so for the SQ model, we try to learn the function, this f star, using queries in the form of, so there's some nonlinear function phi applied to x and y. X is my data, y is the labels. And so of course, this is a population version. This is expectation. But in reality, we have access to a noisy version of this expected query. So in the SQ model, this noise is, the restriction of the noise is that the magnitude is at most tau. Okay? So I want to evaluate, so think of this as some kind of population gradient. But what I actually get in practice is a noisy version of it, where I know it deviates from by at most tau. Okay, and from the previous slide, we know that we can make a further restriction to the class of query, which is that we can restrict this phi to be correlational. Okay, by that I mean, so instead of looking at generic functions of x and y, we'll look at functions that only where we're not allowed to change y. We can only evaluate the correlation, okay, between some function phi and y. Okay, so this is called a correlational statistical query. Okay, so basically, so these in both of these models, the tolerance tau is the noise tolerance is defined in an adversarial sense. So this q tilde can the noise can be arbitrary as long as it does not deviate from the population value by tau. So to translate this to a sample complexity, what we typically do, this is a heuristic, is to equate this tolerance tau with the IID concentration error. So this is so tau is roughly 1 over square root of n. Okay, so this is how we get a sample complexity lower bound from these SQ models. Okay, so these are prior results telling you that if you want to learn a polynomial polynomial single index model with information exponent k, and you restrict the number of query to be polynomial, so you don't allow a neural network with exponential width, then for the correlational query model, you're going to need n that's greater than d to the k divided by 2 samples. So indeed, the information exponent plays a role here. Okay, but if you do not place this correlational restriction, if you look at the full SQ model, then actually this n equals d sample is sufficient. Yes, that's a question.
What is the dependence on tau?
So tau is, so we translate tau to sample complexity.
This is for tau equals to 1 on root n.
Exactly, yes, yes. So I'm already stating this in terms of n, yes. Dependence on the number of queries, basically, this holds for any polynomial number of queries. So basically, you see this divide. So for CSQ learner, this information exponent does it seems to be a fundamental barrier. But for SQ, this is not the case. Okay, and this is perhaps not too surprising because this is a much larger class of queries. And in particular, there's one observation is that there's one kind of query that SQ can clearly make use of, but CSQ cannot, which is that SQ can apply some nonlinear transformation to y, right? Whereas in CSQ, you cannot change y, but you can define your function phi that's act on x. Okay, so this additional degree of freedom that you're allowed to transform y, this turns out to be key, the key to lower the sample complexity for SQ learner. Okay, any other questions? Okay. All right, so just to sum up, so this is the current where we're currently at. So to learn a single index model with degree p and information exponent k, for kernel model, we need d to the p samples, so this is bad. And if we do one pass SGD, this is a result by Benarouche et al., then the sufficient sample complexity d to the k divided by k minus 1, where k is the information exponent. Okay, and the CSQ lower bound is at d to the k divided by 2. Okay, and this lower bound can be matched by a smooth version of SGD. Okay, whereas for the SQ lower bound is at this at order d, which is also the information-theoretic limit. And there is an SQ algorithm by Chen and Mecca that actually achieves this information-theoretic limit up to polylog factors. Okay, so this is the prior results. And so for this talk, there will be 2 parts. The first part is we will try to show that with some cheating, SGD can already implement SQ instead of CSQ So we can make SGD, we can derive a sample complexity of SGD that's close to the information-theoretic limit. Okay, and for the second part, we'll be looking at sort of a more difficult task, which is we have a sum of a lot of single index model. So this is, think of this as a two-layer neural network, where the number of single index model will diverge with the dimension. Okay. All right. Before I present the results, this is a very meta comment here. So I guess in the deep learning theory, in the neural network theory literature, there's often we see the two different kinds of perspective. One driven by phenomena, so where the goal is to try to precisely understand what happens in natural training. Right? So here, we do not aim to show that neural network can learn a very large class of functions. Instead, we try to have some understanding, some description of certain interesting phenomena, such as non-monotonicity in the risk or some phase transitions. Okay? And there's also another perspective driven by learning guarantees, where the goal is to try to establish, to show that neural network efficiently, trained by gradient descent, efficiently learns a large class of functions. But in order to establish these statistical guarantees, we have to make a certain algorithmic modification. So we will not be looking at the most standard SGD algorithm that's used in practice. And so in other words, we allow ourselves a certain amount of cheating, and this will be where this talk is at. Today. So of course, these are not conflicting, right? So ultimately, it would be nice if we can show that if I train a transformer using Atom, we can achieve AGI, but currently that is beyond reach. So we have to make some certain compromises. And so I'd like to tell you what cheating we do on the architecture and the algorithm. So the architecture that we will look at is a two-layer neural network. Okay, so this is so we have two sets of trainable parameters. The first layer weights W, and there's some bias units B, and then the second layer A. Okay, so and the sigma is a nonlinearity. So this is a standard architecture. But what's not so standard is that the activation function cannot be like ReLU or a commonly used activation. We need to randomize the activation function so that the Hermit coefficient of this activation function is non-vanishing up to a certain degree. So this will be important to achieve strong recovery, to achieve a non-trivial overlap with the target function. Okay, and also here we're going to fix this bias unit. B, we're not going to train it. Okay, so this is just for the purpose of we're going to use this additional randomness from the bias unit to approximate the link function. Okay, so this is the architecture. And for the training algorithm, we will not be looking at the most standard SGD training, like this end-to-end training. We're going to do layer-wise training. So we're going to first train the first layer parameters, W. Okay, and the hope is that the first layer, W, is going to find you the direction, this index feature, theta. And after that, we're going to train the second layer, A, to fit the link function. Okay, so we have a two-stage kind of training. And for the first half of the talk, actually, for the when we train the first layer weights, we're actually going to have a specific way to reuse the training data so that we get some non-correlational information. Okay, so this is the cheating that we're going to do for both part of the talk. Okay, so we do not explicitly use SQ algorithm. There's no spectral initialization, et cetera. This is still gradient descent training on two-layer neural network. Okay. All right. So let me. Okay. So for the first part. The motivation is the following. So previously, we talked about this correlational statistical query, and the observation is that if gradient descent is mostly using the correlation term in the squared loss, then the bottleneck will be the CSQ, will be, the CSQ lower bound, which is given by the information exponent. Okay, but so in the context of phase retrieval, it is well known that if you allow nonlinear transformation T to apply to my link function, if you allow for any arbitrary nonlinear transformation, then I can lower the information exponent of sigma star to 1 or 2 for any polynomial link function. Okay, so this is saying that so of course this is something you cannot do with a correlational query because you have to apply a transformation to Y. But it is well known that if you find the right transformation, T, then for any polynomial link function, I can reduce the information exponent to at most Y. Okay. These transformations are typically constructed using certain thresholding operations, so to focus on the tail of the polynomial. Okay, so the natural question, in order to make SGD work close to this SQ lower bound, so basically the question that we ask is, can SGD on the squared laws implement this kind of nonlinear label transformation? Okay. There's a very nice observation from a work by Denny et al., which is the observation is that essentially if you reuse a batch, okay, if you reuse the same training data, then this will give rise to some higher order non-correlational information that essentially implements this kind of transformation. Okay. So just to give you a very quick sketch, so let's consider taking two consecutive gradient descent steps on the same data x and y. Okay. And I'm going to omit the initialization, so I'm starting from 0. So basically, so at the second step, what's going to happen is that you'll be adding the gradient that's evaluated from the first step, W1. But this, because you're using the same data, okay, so what you're going to see is that there will be two terms in the gradient. So the first term is going to look like a correlational query. Okay, so it's x times y. But there's also going to be a second term that does not look like a correlation term, because here, this y is inside of some nonlinear activation function sigma. Okay, so this term is not CSQ. And in most of the prior analysis, we look at online SGD. Okay, so this is Benarouche et al. The many prior works. In which case, because online SGD for the two consecutive steps use a different use a different x. So so here, if you use a different x, then the difference is that so you're going to get an inner product of x and x tilde, where x tilde is a new data point. And this is going to be square root of d is smaller than the norm of x squared. Right? Okay, so, and the other observation is that this second term, this non-CSQ term, scales with eta squared, okay, whereas the first correlation term is scales with eta. So in most of the prior analysis, we choose eta to be sufficiently small so that we treat the second term as noise. And we use the correlation term to learn the target function. Okay? But if we do this, then it's a CSQ complexity that will matter. So basically, the goal of this work is to try to take a learning rate that's not too small, such that this term does the heavy lifting. And this term can, to some extent, implement this nonlinear transformation because this activation function sigma is doing some nonlinear transformation to y. Okay. Does it make sense? OK. So the goal is to basically show that by reusing a batch, we can implement this nonlinear transformation that lowers the information exponent, so then we can learn close to the information-theoretic limit, or the SQ lower bound. Empirically, this is sort of we have this verification that so if we so here I'm plotting the performance of online SGD versus the gradient descent on the same batch. Okay. And this x-axis is the dimension, and the y-axis is the sample size. I'm learning a function that's a degree 3 Hermite polynomial, which has information exponent 3. Okay, so if your algorithm is CSQ, you will not be able to learn this using linear and D samples. Okay, but so indeed for online SGD, using n equals d squared sample, you don't even get weak recovery. Weak recovery means that you have a non-trivial overlap with the ground truth direction. But for the same batch gradient descent, you see that you kind of this scaling looks like n equals d. So it's, perhaps there's some log factors, but essentially you can achieve small generalization error using just linear and D samples. Okay. So we cannot really analyze this the same batch gradient descent as much as so this requires some. I'll explain the difficulty later. So instead, we use this weird algorithm where we resample a batch in every 2 steps. Okay, so we in online SGD we resample in every step. Here we need to take one more step on the same data to get this high order this non-CSQ term. Okay, so this is the algorithm. Basically, the most important line is labeled in red. And also, we use some normalization, essentially some kind of spherical gradient update to stabilize the dynamics. Okay. All right. And the main theorem that we can prove is that for this SGD-based algorithm, if you run this on a 2-layer neural network with some appropriate activation that I'll specify later, you can achieve epsilon generalization error using roughly d times epsilon minus 2 samples up to log factors. And the width of the neural network is also only scales as epsilon. So you can work, this can work with a very narrow neural network. Okay. So this algorithm and the architecture is almost agnostic to the target function, but it's not completely agnostic because we need to know the degree in advance. So we need to make sure that the student model has non-vanishing Hermite coefficient all the way up to something that relates to the degree of the target function. So we still have to cheat. We still have to assume some prior knowledge of the target function. But and this here I'm hiding in the big O notation constant that depends on the degree, and it can depend exponentially. Okay, so when we take the large D asymptotic, this is OK, but we cannot basically. This will be not very efficient if the degree of the function is large. Yes.
You said you first train the first layer and then the second one?
That's right.
Train roughly the same amount of time both?
The second layer training, you can train it for much shorter time. So this complexity is mostly bottlenecked by the first layer. Right? Yes. So yes, the second layer, we only need to train it for something that's proportional to epsilon, basically. Yes, that's a good point. OK, and a side remark is that there's a concurrent work that's also showed a similar sample complexity, but for weak recovery, also using this weird scheme of resampling a batch in every 2 steps. Okay, all right. So as promised, this puts us here, right? So this is with reuse batch, we show that this SGD can actually work, can learn this single index polynomials using O tilde D samples. And this is also the rate achieved by SQ algorithm that's specifically tailored for this low-dimensional target function. OK.
So the algorithm of the CM20 algorithm,
yeah.
that one needs no P as well?
That's a good question. So that I don't think there will be some constant that also depends on P, and I think this dependence might also be exponential. But right, I'm not entirely sure if they actually needs explicitly no P to in the algorithm itself. So in our case, we need to know P because that's how we need to make sure the activation function matches the degree to some extent. Yeah. So.
Your experiment was for normally.
Oh yes, this experiment is ReLU.
Okay.
So so this is not using the special activation function, and the algorithm is also different. This is just end-to-end training. Yes, but this we can't prove. Yes. OK. All right, and I'll just quickly go over the key ingredients here. The first observation is this is something I already mentioned earlier, is that basically the first thing we show is that if you give me any polynomial link function, I can find a monomial transformation, meaning that I can raise this link function to the ith power. There's a typo here. This is sigma star, such that the information exponent is at most 2. Okay. In fact, it's only going to be 2 if the link function is even, because for even function, no matter what transformation I apply to it, it's still even, and even function has information exponent 2. Okay. So basically, after appropriate monomial transformation, the information exponent is lower to 2. Therefore, we only need to analyze online SGD with this batch reuse schedule up to D log D samples. Okay. This is the analogous to phase retrieval. So why is this monomial restriction relevant? It's because we can easily extract this monomial transformation by simply Taylor expanding the nonlinearity. Okay. So this is how we get this. So assuming that this nonlinearity has non-vanishing degree up to is non-vanishing up to a certain degree, then we can guarantee that this transformation, we can always find this degree of transformation that works is always sort of embedded in my activation function, and we can isolate it. Okay. And that's the second ingredient, which is that basically for weak recovery, we need this activation function to have to satisfy some kind of non-degeneracy assumption. But this assumption is satisfied for basically with probability 1 with activation function where the coefficients are drawn from some compact domain. But for strong recovery, this is where we use a randomized activation function. For strong recovery, we need the sign of the activation function to match the sign of the target, the Hermite coefficient. The sign of the Hermite coefficient needs to match that of the target link function. And for this, we basically randomly choose a sign for each of the each beta I, this coefficient. And this is actually where the exponential dependence in CP come from, okay, because this is randomized. Okay. All right. guess I'll quickly mention a few future directions here. One is that, so again, this is the algorithm that we use is rather, it's not entirely standard. It would be nice if we can show like standard end-to-end training with both layers with the, for example, if we just do empirical risk minimization on the same data, we will also get the same statistical efficiency. And it would be nice if we can have some kind of dynamical mean field description for this same batch training. And the main difficulty is that we need to go beyond finite horizon, right? So we need to run this procedure for at least log d time. But the nice thing is that because of this the existence of transformation that lowers the information exponent to 2 for any polynomial link, there's also no reason to go, there's not much reason to go beyond log d time, right? So if you can do the same, if you can run the gradient descent for log d time, you can essentially learn all the polynomials. Right? So there's no, you don't have to worry about going even further in time. So if there's a way to handle DMFT up to log d, I think this might give a way to precisely describe the just basically learning arbitrary polynomial single next models. OK, and for the interest of time, I'll skip the other part of the open problems. OK. Oh, OK. I still have, I think, because this is only the first half of the. OK, all right. So I'll need another like 45 minutes. No, it's OK. All right. So for the second half, we'll be looking at a slightly different model. It's still based on single index model, but now we're gonna we have a lot of single index model. We're gonna look at a sum of m of them. Okay. So this is, I think, in statistics, this is sometimes called a ridge combination because each of the single index models is a ridge function. So we look at so now the target function is defined as the average over m ridge functions. So it's called ridge combinations. Just from this notation, you can see that this is basically a two-layer neural network. Right? So this is a two-layer neural network, whereas each neuron may have a different nonlinearity, and each neuron is pointing at the direction theta m. Okay, and each neuron, we're going to assume it has degree p and information exponent k, just like before. I guess the main difference between, this model will be a subclass of the standard multi-index model. Right? The multi-index model can look at basically m coordinates, but it does not need to have this rich separable structure. So this should be a class of, so if you have an algorithm that learns multi-index model, you should be able to learn this. But the catch is that most of the prior algorithm that learns multi-index model assume m is a 1 as d equal to infinity. Okay, so basically these are you are still learning low-dimensional function. It's just that it's beyond single index model. Whereas here we allow m to grow with d. Okay, with this exponent gamma. You might notice that here we have a 1 over square root of m prefactor. It's kind of like a CLT prefactor. So the reason we have this is that we assume each of the target neuron, or we're going to refer to this to as one task, to be sort of orthogonal to one another. Okay, so you can think of them as sort of draw uniform on a sphere. Okay, so in this case, if you have m of them, then the prefactor to get f star to have unit L2 norm will be 1 over root m. Okay. So why do we consider this model, this sum of a bunch of single index model? So the first is, of course, to have to be able to learn a two-layer neural network that's not too narrow. Right? We want the width of the neural network to grow with the dimension. Okay, and the other motivation, this is more on the LLM side, which is that it seems like, so when you train these large models, it's been observed that this phenomenon called skill localization, where you can find a lot of different skills that simultaneously acquired in pre-training. And so here, this is a very idealized model for that. So basically, the pre-training phase will be to learn the first layer parameters. And after that, you can fine-tune the second layer weights so that you can adapt to each of the individual skills. And this large M asymptotic is essentially indicating a regime where the number of skills, the number of tasks is very large. Okay. All right. So we asked two questions. First is, can we use gradient descent? So can we use the same algorithm as before, gradient descent training of a two-layer neural network? Can we learn this function? And two is that, so now this is not a single index model anymore. So we will have to basically reprove the CSQ and SQ lower bound. Right? So what is the computational hardness of learning this ridge combination? OK. So I'll start with the complexity of SGD. So here, we do not use this batch. We do not reuse the training examples anymore. We will just be doing the online SGD algorithm. And the theorem states that basically, if you if I have a two-layer neural network that's wide enough, in the sense that the width needs to depend. So M is the width of my student network. Okay, so this N is the width of the student network, and M is the width of the target function. The student needs to have a width that sort of depends on M. Then this is the number of samples you need to achieve epsilon generalization error. It's going to scale as M times d to the k minus 1. And also, there's another term that comes from strong recovery that's M times d epsilon minus 2. Okay, so an observation is that if you remember in the previous single index case, online SGD gets you a rate of d to the k minus 1. Right? So this is a sample complexity from Benarut et al. So here, this is essentially saying that the sample complexity of learning this additive model is the same as learning M single index model, which makes sense because the model itself is a sum of M single index models. Right? Okay. So let's just quickly compare this against the other algorithm. So for kernel ridge regression, again, the sample complexity will be d to the p, but p is a degree, which is always larger or equal to the information exponent. So here we always gain something. So the gradient-based training is going to outperform kernels. The more interesting baseline is this prior results of gradient-based training for multi-index models. Okay, so basically, there's been a lot of studies on feature learning in neural networks that shows that training the first layer parameters is going to localize the neurons into the rank M subspace. Okay, so after training the first layer, your first layer, your parameters will adapt to the support of the target function. So the target function spans M directions. So now you, after training, your student model should also span the M directions. And after that, when you train the second layer, you're essentially doing kernel model, but now on this M-dimensional subspace. So that's how you gain improvement over kernels. Okay, so the complexity usually scales as follows. It scales with d to the k. This is the complexity of finding this M-dimensional subspace. And also, there's also M times M to the p. This is the complexity of doing kernel model on top of this M-dimensional subspace. So in prior works, this M is 01, so then you get this d to the k sample complexity, as in the single index case. But you can see that here, because we allow M to diverge with d, now this M to the p term can be dominating. Okay, so it might be large. Whereas the rate we get here, it always scales linearly with M, and the degree of the target function does not appear here. Okay, so this will be the advantage of this new analysis. And the way we show this is that essentially we have to show a different kind of localization. Instead of showing that the first layer parameter spans M directions, this is not sufficient because M is very large. We need to show that basically for each target neuron, for each single index task, there exists some pseudo neuron that's going to align almost perfectly with it. Okay, so this is pictorially, so here I have two teacher neurons that are pointing in these two directions. And here are the trajectory of the student neurons. Okay, basically for each, think of this as kind of, it's almost like a lottery ticket thing. So for each direction of the target function, there will be some neuron that finds it. Okay, and after that, training the second layer is going to give you a statistical complexity that's independent of the degree. Okay, does that make sense? Okay. All right. So I have 3 minutes, so I'll talk about the computation lower bounds here. So basically, the sample complexity we get here is essentially suggesting that the complexity of learning the sum of M in a single index model is the same as the complexity of learning M single index model separately. So it's N times d to the k minus 1. Capital N, this is the width of the student model. Okay, so it needs to scale with the width of the teacher model. This is actually, sort of this intuition aligns with the CSQ lower bound. Okay, so for CSQ lower bound, what we can show is that if you restrict yourself to polynomially many queries, the sample complexity needs to scale with M times d to the k divided by 2. So if you remember, for single index model, the CSQ lower bound is d to the k divided by 2. Okay, so this is M times that. So this means that for CSQ model, so if you learn an additive model with M tasks, this is the same as just learning M single index models. Okay. So this is rather intuitive. the unintuitive part will be the SQ lower bound, because for SQ lower bound, if you remember, we have an algorithm, right, so that actually learns a single next model using D samples up to polylog factor. So basically, based on this intuition and the SGD upper bound, you would imagine if the complexity, if the SQ lower bound is also the same as the SQ lower bound of M single next model, then here you should get M times D, right? So it's M times the complexity of learning one single next model. I don't know what happened. Oh, all right. Okay. All right. But this is not the case anymore. So basically, what I can show is that this for the SQ lower bound, this n needs to scale with m times d to some power rho, where this rho can be made arbitrarily large by choosing the degree and the information exponent. But arbitrarily large, I'm not saying that we should choose p to grow with d. Okay, so the degree is a constant, but this can still be taken arbitrarily large by making the constant large. So essentially what this is saying is that the SQ complexity of learning this additive model would not be the same as learning M single next model separately. Okay, so this is the part that's not very intuitive. Yes?
But this lower bound is smaller than the one above?
Yes, because SQ is, you have a larger class of query, right?
No, I understand, but you're saying rho can be arbitrarily large, right?
Yes.
But, so in that case, doesn't your lower bound have
That's a good point, yes. But rho can be made arbitrarily large by changing P and K.
Oh, I see.
So, but here I'm not specifying.
Constants there.
Yes, I'm not specifying how much it changes. So it's possible that to make rho large, you have to take K to be 1,000, where this is, yes. So just to give you a quick intuition of why, why this SQ lower bound is it does not behave as the sum of a bunch of single next models. So essentially, the way we prove this is that first we show that so this is like the converse of the previous claim we have when we try to lower the information exponent. Previously, we state that if you give me a link function sigma star, I can always find some polynomial transformation that lowers the information exponent to 2. Right? So that's part one. Here, this is like the converse. This is saying that if you tell me in advance what polynomial transformation you use, okay, if you tell me that you can use polynomial transformation up to degree I to try to lower the information exponent, okay, then I can find some weird link function g such that all these polynomial transformation up to degree I fails. Okay, so this is essentially this is telling you that there will be, so if you take I to be 2, essentially this is saying that there would exist a link function such that squaring it does not lower the information exponent. And these polynomial link functions, we can construct them explicitly, but they look rather ugly. Okay. So now the question will be, the natural question will be, why is this sufficient, right? Because remember, SQ, I can apply any L2 transformation. It's just why do I restrict myself to low degree polynomial transformation, right? Why is that sufficient to rule out the possibilities that SQ learns this? And this is actually where we use the fact that there is a lot of tasks. Okay, so essentially the reason we can restrict ourselves to low degree polynomial transformation is that because M diverges with D. So asymptotically, if you apply some SQ, some statistical query to my one single next model, because M is large, then ultimately what you get, the effect you have on this one model becomes low degree. This is just a Taylor expansion. Okay, because does that make sense? Because I have so many tasks, and there's a 1 over square root of M prefactor. So you apply the statistical query outside of F star, but now when you localize it into one task, one single next model, it's essentially it's Taylor expandable. Okay. And just a side remarks, for those of you who's familiar with this notion of generative exponent, so basically we know that there actually already exist link functions, sigma star, where any transformation cannot lower the information exponent to 2. So you can also use this to imply to infer computational hardness. But here we restrict ourselves to polynomials, right? So and from part 1, we know that polynomial link function always have generative exponent less than 2. So if I'm looking at one single next model, there's a way that I can lower the information exponent. But this is not possible when capital M is large, when I have a lot of tasks. Okay. So what this implies is that essentially, so here's the rate we get. Information theoretically, because I have M tasks, capital M tasks, each task have D parameters. Information theoretically, I need M times D samples to learn this. There's a SQ lower bound that's M times d to the rho's power, where rho can be made large. And there's a CSQ lower bound that's m times d to the k divided by 2. Now the information exponent plays a role. We cannot match the CSQ lower bound currently because we use one pass SGD. So the rate we get is m times d to the k minus 1. But this rate is still better than what you naively, if you naively use kernel, you get d to the p. Okay? And if you look at this, at the left side of this figure, essentially this is just a computational to statistical gap, in the sense that so information theoretically you need m times d sample, but any SQ learner, if you restrict the algorithm to be in the SQ class, then this gap can be made arbitrarily large. Okay, so there will be a regime where information theoretically you can learn this, but SQ models cannot. Okay. All right, so I think I'm running out of time, so I'll stop here.